x1 prime r times. So I didn't put of s here. If it has a bar on top, that means Laplace transform, and it's only of s. Okay? S and t, the t variable, never mix. You shouldn't have together both. If you ever have together both, you have messed up. So that's the left-hand side. And then a Laplace transform the right-hand side. The first term is minus 0.11 times x1 prime. Remember, Laplace transform is an integral. Any constant factors out. So this is going to be the same as Laplace transform of minus 0.00 of minus 0.0111 times the Laplace transform of x1. So the Laplace transform of this term is simply minus 0.111 x1 prime bar. Rian, question? No, you frown, so something didn't click.
No, you're fine. Go ahead.
Okay. The next term, and I'm repeating again, the Laplace from the right-hand side, because of the linearity of the integral, is the sum of the Laplace transform from the first term, plus Laplace transform from the second term, plus Laplace transform from the third term. So what's the Laplace transform from the second term? Well, again, the constant factors out. Remember, all the primes are variables and functions of time. So in this case, the f of t is the u prime. So we'll get plus 0.0018 u prime. Similarly for the last term, okay? Now I have an equation that is algebraic for x1 prime bar. I can solve for it. Let's do that. Trivial algebra. Move this guy to the left. And also move the one that doesn't have x1 prime bar to the right. Will give us the right intermediate step. I get s, and from here plus 0.111 x1 prime bar equals. This moves to the right, x1 prime of 0 plus 0.0018 u prime bar plus 0.0111 d1 prime bar. So from here, let us solve for x1 prime bar.
Should I say STO? Oh, S plus 0.0. No.
What is the STO?
In the parentheses, it says S plus 0.0111.
That's a plus. That's not terrible handwriting. So, we divide by the parentheses to solve for x1 prime bar, and we get x1 prime bar equals x1 prime of 0 over s plus 0.111 plus, and I'll write it this way, 0.0018 over s plus 0.111 times u prime bar plus 0.0111 over s plus 0.111 d1 prime bar. Now, even though that won't lead us to the transfer function, it will lead us to the big implied assumption. Let's look what conclusion we can get from this equation for x1 prime of t. So I have here an equation, I have solved for x1 prime bar. Let's see what conclusion we get for x1 prime of t. So this is x1 prime bar. How do you think I will get some conclusion for x1 prime of t? What do you think?
Graph it.
X1 prime bar, graph what? Against
I
what?
don't know. Sometimes that works.
But what? I have x1 prime bar. How am I going to get some for x1 prime of t? If there are two, maybe I have on the board that can be used.
Make one equal to 0? I don't know.
Is there a tool on the board that perhaps I can use? I'm looking for one word.
With laws?
What? Yes, thank you, Alvin.
What?
The dictionary. Someone say it? You need to speak louder if you. Someone said before, Alvin, sorry, but dictionary. Now I need to go. I have x1 prime bar. Okay, I need to go to exponent of t. Use the dictionary. Going now from great to English. So, remember the Laplace inverse is also a linear operator. So the left-hand side clearly will give me x1 prime of t. Right-hand side. This term, remember, what is x1 prime of 0? It's a number. It's whatever was the CA deviation at time 0. Okay? If the actual initial concentration was 0.3, okay? Sorry, 0.03, 0.03, the nominal value is 0.02, the difference is 0.01, x1 prime of 0 would have been 0.01. Okay, so x1 prime of 0 is just a number. So, can we use the dictionary for getting this term? Back to the time domain. Is there anything in the dictionary that can be used? And
The first term?
the very first term. What's that? That's x1 prime of 0 times 1 over s plus 0.11. Do you have something that looks like 1 over s plus 0.11? Yes, 1 over s plus a to the k, use k equals 1. Do you see that? Am okay? So, for that term, it will be x1 prime of 0, the number factors out, times the L inverse, let me write it, and then I'll use the dictionary, of 1 over s plus 0.11. Now, the next terms, this one, what is your prime bar? It varies. Unless I give a specific u prime bar, I cannot invert the time domain. The inputs continually vary. x1 prime of 0 is fixed, that's a number. But x1 prime bar, u prime, x1 prime, u prime, d1 prime, all those continually vary. So I cannot put something for u prime bar, and also, mistake I hope to not see from you guys. Remember, the Laplace transform of a product is different from the product of the Laplace transforms. Also, the inverse of a product is different from the product of the inverse. So you can't say that the inverse of this is the inverse of that times u prime of t. That's a serious bad error. One question.
Why is that 1 inside the Laplace?
Because I took x1 prime out of the common factor, so that's x1
Oh,
prime.
okay. Okay, got it.
Okay. Anybody else? All right. So the second term, I have to say simply L inverse of 0.0018 over s plus 0.111 u prime bar, and I can't do anything about it. And important, this is different from the inverse of this times u prime of t. Similarly, the last term,
Why'd you pull it out in the first term?
Because it's a constant. So I can pull it out.
Yeah, but isn't that number, the 0.0018, a constant also?
I could have pulled that out, but there's no purpose.
Okay, alright.
I'm not going to achieve anything.
I thought there was like something
No.
you wanted us to see.
For this one it is because I can go to the dictionary, I have 1 over something in the dictionary. That's why I pulled it out.
Okay.
To immediately see how it goes in the dictionary. So, okay? So, let's continue here. So follows that no matter what my system is doing, whatever the disturbance is doing in response, the manipulated input is doing, I will always have x prime prime of t. So what's the inverse according to the dictionary of this? As already was said, we've used k equals 1 and a equals 0.111. So with k equals 1, what is the left-hand side? For k equals 1, I have t to the 0, which is 1, over 0 factorial, which is 1, e to the minus at. So this will simply give me e to the minus 0.111 t. John notes convincingly. So that term gives me x1 of 0 e to the minus 0.11. And then I have whatever is the inverse of 0.0018 over s plus 0.111 u prime bar plus whatever is the inverse of 0.0111 over s plus 0.111 d1 prime. Okay. So that's what x1 prime of t is going to be. Now, here is a key concept. I'm designing a feedback control system not for the next minute. I'm designing, this is controllers that are staying for months, for years, etc. So I'm looking at long-term operations. Let me ask you something. After 10 minutes, how big is this term?
Small.
It's about e to the minus 1, 1. Okay? After half an hour, it's going to be e to the minus 3. Someone with a calculator, what's e to the minus 3.33?
It's very small.
Yeah, how small? Well, let's just calculate after. Well, okay, e to the minus 0.333.
0.71.
That big still?
0.0357.
That's what I was. Okay. I'm going to take Jarrett Sands. E to the minus 3.33. Okay. So the answer was about 0.07? 0.03. 3%. After 1 hour, e to the minus 6.66.
0.00128.
So 0.001. You can see that this term becomes immaterial very soon in terms of the purpose of my controller design. So if I assume x1 prime of 0 is 0, it's not that I really believe x1 prime of 0 is 0. That's not the justification. The key concept of transfer function doesn't require that my initial time, that my initial condition is close to the nominal steady state. That's not really required. Because no matter how big this guy is, very soon this term will be 0, no matter how big this guy is. Do you understand that? So, the this soon becomes 0 no matter how large x1 times 0 actually is. So I'm not introducing a significant error in terms of how my control will be performing long term. Remember, I'm designing something, the disturbances come all the time, so I need to be changing the manipulated input all the time to be filing them. Set points may be coming in the future, set point changes and so on. So, here is the big implied assumption. The word transfer function always has the implied assumption that all deviation variables at time 0 are 0. In other words, at time 0, we assume we are at the nominal steady state. Not because we really are, but because, as you see here, very soon it will be irrelevant how far we were from the nominal steady state. Very soon, my system performance, my system behavior is going to be identical to what it would have been had we started exactly at the nominal steady state. The concept clear? So that's the implied assumption. So we will be assuming that. So the same, I did this in this example, but this holds for any state variable. Okay? Always state the initial condition that you get from the dictionary, that f of 0 will be multiplied by e to the minus something t. For a stable system. I should say that for a stable system. And normally we have open loop stable system. Okay? So we'll be assuming that x1 prime of 0 is 0, and in general, all deviation variables at 0. Even if very different. And that's the big implied assumption. The moment that you see a transfer function model, that has that implied assumption behind it. Okay? With that assumption, I can rewrite, let me rewrite this equation here. So I had equation 1. Let's call this equation 2. Sorry, put a 2 here in your notes. Go back and put a 2 here again. Right, this equation 2. Okay? So this is the implied assumption. The implied assumption for all transfer functions. So with the implied assumption, and I'll abbreviate it as IA, so 2 implied assumption, okay? IA stands for implied assumption. Becomes that x1 prime bar equals 0.0018 over s plus 0.111 u prime